Hi, today we're going to start part 3 of our Wednesday lecture here on YouTube. And this part will cover chapter 2, beginning of chapter 2. Chapter 2 is going to focus on the electronic structure of the atom. Now, there are 3 really big reasons why we want to understand about the electron, one of our subatomic particles that we introduced during an earlier lecture. And of these 3 reasons that we're going to discuss, I have them listed here. We'll be going into them over the course of this, over the series of this course through several later lectures. One important feature of the electron and how it affects atoms is that it influences chemical bonding. It also influences the shapes of compounds that we're going to be discussing later. And further down the line, we're going to understand about chemical reactivity. Each of these 3 features are really dictated a lot by the electronic structure of an atom, specifically, and more importantly, as we'll learn later, are valence electrons. So today, we're just simply going to begin discussing a little bit about how we can learn more about the electron. So in section 2.2, if you look at the title of it, Section 2.2 discusses the nature of light. Big question might come to mind. Why are we learning about light when Dr. Patton just said we want to learn more about the electron? Well, the reason why we're going to study a little bit about light and learn more about light is that subatomic particles, like the electron, share a lot of properties that are similar to light. And we're going to learn a little bit later that light has a name to it, the particle nature of light. We call them photons. And since the electron shares properties with light, we as chemists, as scientists, physicists also, and other scientists, we use light as a tool to provide us with information about the electron. In other words, we use light as a tool to make measurements regarding the electron. And this is in a field of an instrumental analysis and quantitative analysis that I teach. This is in the field of what we call spectroscopy. If you take a more advanced class, you'll probably spend a whole course discussing about spectroscopy. So an important property of both light and the electron is that they have what we call a particle-wave duality. Now, what particle-wave duality implies, or what it means, is that light and the electron being so small, the best way to describe them is using properties that are both associated with a wave and a particle. So if we understand a little bit better about waves, particles, light, we're going to learn a little bit better about the electron. So we're going to begin by discussing a little bit about the wave characteristics of light. So let's discuss what light is. And a term that you probably may be familiar with or have seen. If we consider light itself, light has been described as an electromagnetic form of radiation. So when we say it's electromagnetic, what we mean is that if we look at this in 3 dimensions, and this is how we would look at it on a 3-dimensional scale. On one axis, we have an electronic component, so we'll call this E, electronic. And we would envision this form as a wave propagating or moving in the direction to the right side of this dry erase board. Now, if we look at this axis, and this is why we call it electromagnetic, we just simply say this is an electromagnetic wave, EM. There's also, in the other axis in 3 dimensions, there's a magnetic component. We'll call that M. And it also propagates in a particular direction, depending upon where our light is initiating at. So some of the properties of light that are important for helping us to understand about it in terms of its wave nature, we're just going to look at the electronic component. And one feature of a wave is that it has an amplitude. So let's take a different color marker. Let's use my red one. Amplitude, and that would be the height of the peak of one of the waves, and that's called our amplitude. Amplitude is simply the peak height of a wave. It also has a length associated with the distance. Length is the distance between two peak points. Use my green marker. No, go back to black. Black's working. And this is real important here, so I'm going to use black to make sure everybody understands it. The distance between two peaks is known as wavelength, and we actually have a Greek letter for it, lambda. So we call this wavelength. Wavelength is the distance between two peaks. And we give a Greek symbol of lambda for that. And since it's a distance unit, wavelength is normally going to be in meters, centimeters, or in a lot of cases, we're going to be using the nanometer. 1 nanometer, as you recall, is 10 to the negative 9th meters. That's important, some important properties of waves. There's another important property of light, since it's propagating or moving in one direction. Light also has what we call frequency. So let's look at what we mean by frequency. In frequency, we're going to give that a Greek letter also. This is the letter nu. It looks sort of like a V. Frequency. So to understand a little bit about frequency, what we're going to do is we're going to choose a point in time, and let's just choose this position, this point right here. And let's put a little dotted line there. And what we would think of frequency, it's the number of peaks that pass that point per unit time. So it's the number of peaks that pass a point per unit time. Frequency is usually listed in terms of cycles of peaks that pass a point over a time unit. Oftentimes we're going to use seconds. So this could be cycles per second. Sometimes you'll see that. Since seconds is in the denominator, it's the number of peaks that pass per unit time. You'll sometimes see this listed as seconds raised to -1, since the seconds are in the denominator. That -1 indicates that. A unit that we use to represent these, a name, is the Hertz, HZ. Just like Hertz rental car, HZ has units of seconds reciprocal. So those are some important properties of light in terms of length, amplitude, frequency. But also very important about light that we're going to learn is that since light is a propagating or moving wave, it has a speed associated with it. So let's think about speed. So if you took a physics class, or if you run or you have a car, speed is defined as distance of a moving object, perhaps, how far it travels over a certain time interval. So let's think about speed and use what we just learned about waves. Speed, remember, the distance that we measure between two peaks is wavelength. So that's lambda. That's wavelength. Per time, remember, the inverse time units per second is frequency. That's nu. So the speed of a wave is equal to the product of its wavelength multiplied by its frequency. Now, for light, electromagnetic radiation, whatever form of light that we're considering, it has a well-defined speed, and we give that a letter C. C is defined as the speed of light. The speed of light in a vacuum is defined as 3 times 10 to the 8th meters per second. That's pretty fast. Light travels at a pretty fast rate. So if we know the speed of light, C, is constant, if we know the wavelength or the frequency, well, we can figure out a little bit more information about that particular form of electromagnetic radiation. This is a very useful definition of the speed of light. If we know the wavelength of a certain form of radiation and we know the speed of light, we can calculate its frequency. If we know the frequency and the speed of light, which is constant, we can calculate its wavelength. Let's do an example problem. So, a lot of you might have seen these somewhere. These are the little red lasers you can buy in a store. And let me see if I can shine it up here on this board. So if you look at this, notice these lasers have a little laser spot on them. And if you look carefully at this one, this is a red laser. I believe this one is also. So these are two red lasers. Now our cat, man, he really loves those red lasers. He'll chase them all over the place. If you have a cat, you may have actually done this. And if my cat was here right now, I would do that as a demonstration. But since he's not around, we're just going to solve a problem dealing with a simple red laser like this that you'd be able to buy. There's my red laser on the dry erase board. Now, let's write down what's given to us in this problem. So in this example that we're going to work through, we're given some information about a laser such as this that we would use to play with a cat. We're going to use this laser, and this laser, on the side of it, they have a warning symbol. You don't want to put these in your eye because it'll ruin your eye. And they also give you the wavelength. The wavelength of this laser is 650 nanometers. And what we're going to do is we want to calculate what's its frequency. What's the frequency of that particular red laser that I just showed you? And in this problem, and on an exam, or anytime you're doing homework, for this problem, we would need the relationship that the speed of light is equal to wavelength times frequency. Oops, frequency is nu, I'm sorry. And we would find in a table that the speed of light, C, is defined as 3 times 10 to the 8th meters per second. So that would be given to us. We want to determine frequency. Remember, frequency is this value nu. So this is a good example of just using an equation, doing a little bit of algebra, and plugging our numbers in. So let's redefine our frequency. Frequency is defined as the speed of light divided by the wavelength. Okay, now it gets to the point where we just plug in what's given to us and solve for frequency. We're given the speed of light. And we're given the wavelength. Okay, if you plug that into your calculator, you're going to get an answer. And right now, it's not going to be right. There's something we have to take care of. And this is a discussion that we did in our first lecture about using equations, making sure that the units are compatible. Notice that the speed of light is in meters and our wavelength is in nanometers. We need to get them both in the same unit. The one I would do, this is what my choice, I like to report the wavelength not in nanometers. Let's report it in meters. And remember that 1 nanometer is 10 to the negative 9th meters. So let's redefine our frequency is 3 times 10 to the 8th meters per second. This is 650 times 10 to the negative 9th meters. If we put this into our calculator and we use our calculator properly, we're going to get an answer for our frequency. And these are often pretty large numbers. I'm going to get an answer, and I'm going to limit myself to our data here, the wavelength that's listed. We're going to say that this has been measured and it's been reported for this particular laser with 4 significant figures. We're going to report our frequency, 4.615 times 10 to the 14th. And our frequency has units of seconds reciprocal. So the frequency that we got, and I'll write it up here, just so everyone sees it, 4.615, 4 significant figures, and it's limited by our wavelength that's given to us. And our units are seconds reciprocal, and that's because meters cancel out. And that's how we can convert a wavelength of a laser using the speed of light. We can easily determine what its frequency is. We'll pick up in chapter 2 on Friday. Have a nice day.